In conclusion, we designed a digital filtering system to remove specific notes from an input signal. Also, using a DSP, we successfully created a pass-through program, which lays the foundation for the implementation of an efficient filtering system. In the end, a proof of concept for a functional digital filter was achieved with this project. Are there any questions?
What was the passband ripple that you used, and can you discuss what might be, what effect that might have in an application such as an audio system?
The passband ripple we used was 3 decibels. We needed a ripple that was small enough that the frequency, the amplitude of the signal would not modulate too much when the note was passed, and it needed to be large enough so that the filter order would not grow too large.
Yeah, the question about your elliptic filter design, was that a direct continuous time, that is analog design, and then you had to convert to the digital form, or was it a direct digital design?
As you stated first, it was designed in the analog frequency domain and then converted to the digital using a bilinear transform.
Were there any issues or complications in doing that conversion from analog to digital?
The bilinear transform maintains the stability characteristics of a filter. And that is to say, if the filter is designed to be stable in the analog domain, when transformed into the digital domain, it maintains its stability. So, no, there were no issues in that aspect.
Can you explain your justification for choosing minus 40 dB as your attenuation, and also tell us if you ever actually listened to the rejected signal at that level and whether or not it was audible?
Our justification for choosing 40 decibels of attenuation between the pass and stop bands of our filter came from the spectrum analysis we did on the 3rd slide using the input from an actual guitar. If you allow me, I'll return to that slide. Okay, this slide shows the frequencies played from striking the open E string, the lowest note on the guitar. On this graph, the peaks represent the frequencies that compose the signal, whereas down below is static or noise. The difference, the average difference between a part of the signal that you could hear and the noise, which was barely audible, was 40 decibels, which is why we chose that attenuation between the frequencies we wanted to pass and the frequencies we wanted to stop.
In your filter that you mentioned on here, did you actually design a 330 hertz filter, or was it more general that could be used for the rest of the continuation of this scale?
We designed a general filter that could be modified to produce a filter of any central frequency, and 330 hertz was chosen as a test frequency for our proof of concept.
I have 2 questions. First, what would be the effect if this full filter were implemented of playing, say, a diminished 7th chord?
For our project, we only focused on the major scale. I believe that was beyond the range of our research at this time.
Okay. And secondly, with the, you talked about aliasing on one of the slides, and you mentioned that most music is now listened to actually as an MP3 instead of the good old-fashioned vinyl. How would this filter interact with the MP3 encoding routines? Can you speak to that at all?
Are you suggesting that an MP3 player be hooked up to this device rather than a guitar?
No, I'm saying that if you record music through this filter and then run it again into the filter / encoding that happens to produce an MP3, what would be the effect of the two filters in sequence?
If anything, I would think it would improve upon whatever the response of the first filter was. Meaning, if it attenuated a frequency 40 decibels with the first pass, it would attenuate it again through the second. This device, the final goal for this device is to be an effect pedal for the electric guitar, a foot pedal, such as the one shown a couple presentations ago, that can be operated on stage. There are several products that effectively do what we try to do out on the market today. However, one example is a pedal offered by Line 6. It offers filtering effects to the user, but they're not nearly as complex as the one that we're trying to create, and it's not capable of filtering multiple frequencies at the same time. Another product offered through Antares Audio is known as Auto-Tune, which is a software program that actually shifts incorrect frequencies to the correct frequencies. It doesn't eliminate input, it moves it to the right pitch, creating a perfectly tuned copy of the original recording. However, this software is very expensive and is typically only used in studios.
Your answer sort of touched on my question I wanted to ask. Within your filter, do you have a variance built in to handle a correct note that was not played into a pitch that was either sharp or flat?
We allow approximately, for the frequency that we chose here, 330, we allow plus minus 8 hertz of variation within the pass band. This will comfortably cover any bending of the guitar's note, or as well as playing of the guitar that's slightly out of tune. That way the system will still work without filtering out anything that's not a precise frequency. If that answers your question.
Okay, thank you.